Hello, my name is Chris Harris and I'm from Allery Chemistry, and welcome to this video on OCR, carboxylic acids and esters. So this video is going to go through the topic of carboxylic acids and esters, and it is specifically designed for OCR, for the OCR syllabus. So everything in here is going to be information that you need to know for this syllabus and nothing more. So you don't have to worry about, is this on my spec, is it not, because everything in here is tailored to OCR. There is also a full range of videos on Allery Chemistry YouTube channel that has, it's the full range of OCR videos from year 1 and into year 2, and also for all major exam boards, all of the major exam boards as well, which are tailored to that exam board. So please do have a look. They're all for free, so all I ask is that you subscribe to the channel just to give you some support. So that would be fantastic, and you get all the updates as well. And then new videos that's put on. It's constantly evolving and constantly changing, so it's quite a big channel now at the moment. There's a lot of videos on there. So but also, if you want your own private copy of these slides, you can purchase them on the link in the comments box, the description box, should I say, below. So if you have a look, if you click on that link, you'll be able to get a hold of the slides there. And from the TED shop, they're really good value, and they're ideal for revising on the move, on your tablet, smartphone, etc. So just get a hold of them. You get the full range of them. They're all available there. So if you just go and have a look on there. Okay, so like I say, this video is dedicated to OCR, and so it matches the specification. What I would say as well is that these videos contain revision material, but it is really important that you practice the content as well through exam technique. It's just as important as the content, if I'm honest. So, but I have done some videos on Allery Chemistry on my YouTube channel that has information on how you can get the best out of your exam by going through an exam. So there's exam walkthroughs on there. So go and have a look, go and have a browse. There's plenty on there. Okay, so let's start with carboxylic acids. So carboxylic acids have the carboxyl group, which is COOH functional group, which contains both the carbonyl group, which is the C double bond O group, and the hydroxyl group, which is the OH group. And carboxylic acids are named by finding the longest carbon chain, and then we just add oic acid on the end. So it's pretty straightforward. You would have done nomenclature in year 1, for definitely you would have done that in year 1. So it's very similar. All we do is we add oic acid on the end. So there's nothing new there. And when we name carboxylic acids, carbon 1 is always the one with the carboxyl group on it. So the carboxyl group will always be at the end of the molecule. We can't have carboxyl groups in the middle of molecules. They're always terminal groups. So let's have a look. So the first one here is ethanoic acid. The reason why it's ethanoic acid is because we've got 2 carbons here, as you can see, and we've got 3 hydrogens surrounding it, and then we have our carboxyl group here. So this is ethanoic because it's 2, so 2 carbons, ethanoic. The next one, now this time we've made it a little bit more complicated. We've got, count the number of carbons, we've got 1, 2, 3, 4 carbons, so this is butanoic acid, but before that, we've got a chloro group on the 4th carbon, because remember that's always carbon 1 there. So it's on the 4th carbon, 4 chloro, and then 3 hydroxy, because the hydroxyl group is on the 3rd carbon, as you can see there. Okay, and then benzoic acid is with it's basically an arene. It's an aromatic compound. It has a benzene ring, and it has your carboxyl group on the end there. So there are videos. I've done videos to do with aromatics as well. So benzene. So have a look at that if you're not too sure on your benzene chemistry. Okay, so let's look at solubility. So carboxylic acids can dissolve in polar solvents like water, and they dissolve because they can form hydrogen bonds with the water molecules. So here's an example. So we've got our carboxylic acid. This is ethanoic acid on the left here. So there's your ethanoic acid there. And that hydrogen bonds with your water molecules. Now it can hydrogen bond in 2 places. So it can hydrogen bond with your oxygen. So you've got your lone pair of electrons on your oxygen. That'll hydrogen bond with the hydrogen on the water molecule. And likewise, the oxygen on the water molecule can hydrogen bond with the hydrogen on the OH part of the carboxylic acid. So the hydrocarbon part is non-polar. so it doesn't dissolve in water, and the bigger the hydrocarbon part, the less soluble the carboxylic acid is. So what that means is that if you've got a carboxylic acid with, say, 10 carbons attached to it, it's going to be less soluble, a lot less soluble, in fact it would probably be insoluble, compared to something which only has 2 carbons, like the one that you see on there. So the only bit which is polar is the actual carboxyl group. The hydrocarbon bit before that is not polar, and so if most of the molecule is made up of that, then it isn't going to dissolve, is it? Okay. So carboxylic acids are also weak acids, and what they do, just like with any other acid, is they react with bases and carbonates to form a salt and water, but because it's reacting with carbonates, it will also form carbon dioxide as well. So the weak acids, and they dissociate partially to form a H plus ion and a carboxylate ion. So here we go, here's your carboxylic acid, and this will dissociate to form your carboxylate ion and H+. This is exactly the same as any acid would do. When it dissociates, it breaks up into its ions, but because it's a carboxylic acid, it's a weak acid, so equilibrium will lie well over to the left hand side, which is over on this side, so you won't get much of these elements here, so you get a lot of this but not much of this. So equilibrium, like I say, it lies well to the left because it dissociates poorly. So as they're acids, they do react with carbonates, that's CO3 2-, to form salt, carbon dioxide and water. So here's the reaction between ethanoic acid and sodium carbonate as an example. So you can see here that we've got sodium carbonate, which is Na2CO3, forming your salt, water and carbon dioxide. And also, as another example of another carbonate, this is sodium hydrogen carbonate. It's exactly the same. We form water and carbon dioxide and your salt. So you can see that because it's an acid, it reacts in the same way. So there's no difference here. The only difference is we're using a carboxylic acid instead of a mineral acid like hydrochloric acid or nitric acid or sulfuric or anything like that. Okay, so they also form bases, like I say, to form. They also react with bases to form salt and water, like I say, and we'll look at the reactions of them. But also react with metals to form salt and hydrogen. So they react with alkalis, as you can see here. So we've got carboxylic acid reacting with sodium hydroxide, which is your alkali, and that will form your salt, your sodium ethanoate in this case, and water. So there you go, sodium ethanoate is your product. And they also react with metal oxides. So you've got it here. So you've got a metal oxide here. That forms your metal salt to form water. So this is also a base. Remember, your oxides are bases as well, your metal oxides. So these react to form your salt and water. There you go. In this case, it's going to be magnesium ethanoate. And then obviously the final one is they do react with metals and they form hydrogen. So it's acid plus metal forms salt plus hydrogen. So again, we will see fizzing because we've produced hydrogen gas. And you might remember that you can test for hydrogen gas by putting a lighted splint over the test tube and you get a squeaky pop if hydrogen is being produced, because hydrogen is incredibly flammable. Okay, so let's look at some derivatives of carboxylic acid. So these are based on a carboxylic acid but have a slight difference to them. And an example of that is an acyl chloride. So they have the functional group COCl. So instead of COOH, like carboxylic acid, they have a chlorine instead of the OH part. And it contains the acyl group, which is COCl. So these are named in a similar way to carboxylic acids. There's no difference. There's no difference in terms of the naming, other than we put oil chloride at the end. And the acyl group, just like a carboxylic acid group, the acyl group is always carbon 1, and the acyl group will always be at the end as well. It's always a terminal functional group. We won't have it midway through the molecule. Okay, so let's look at this example here. So you can see the similarities with a carboxylic acid. The only difference is, instead of an OH group, we have a Cl group instead at the bottom there. So this example is ethanoyl chloride because we've got 2 carbons and obviously we've got the acyl group at the end. Here's another example. So this is 3,4-dihydroxybutanoyl chloride. So we've got your two hydroxyl groups here, which is one at the end and one in the middle here. So this is always carbon 1. So that's 1, 2, 3, 4. So this is 3, 4 butanyl chloride. And so these are actually made by reacting a carboxylic acid with thionyl chloride. So thionyl chloride, and it with thiol or thiol, means it's got sulfur in it. So this is thionyl chloride. So this is SOCl2. Very straightforward. Carboxylic acid plus your thionyl chloride will form your acid chloride plus sulfur dioxide plus HCl. So this is the way in which we make our ethanol chloride. We just use thionyl chloride, so make sure you're aware of that. Okay, we need to know the reactions of these. Now, acid chlorides are incredibly reactive, and so all the reactions are vigorous reactions, but we need to know what we react them with and what products we make. So they react with water, ammonia, alcohol and primary amines, and each reaction, chlorine substituted, and either an oxygen or a nitrogen is put in its place. So what we're going to do is look at all of the reactions for all four, break it down and see how they react. So let's start with the reaction with water. So when we react an acid chloride with water, we form a carboxylic acid. So we've colour coded this so you can see. So here we've got ethanol chloride, react it with water, and what we form is our ethanoic acid, and HCl gas is produced. Now, like I say, it's a vigorous reaction, and we do produce white misty fumes of hydrogen chloride gas at the end. You've got to be very careful with that because it's incredibly acidic, so this must be done in a fume cupboard. Now, this reaction is a nucleophilic addition elimination reaction. So we're adding on a substance and then eliminating the chlorine at the end there. So that's the type of reaction mechanism that it is. Okay, so the reaction with ammonia produces amides. So let's have a look. There's our acid chloride and there's our ammonia. So we've got ethanol chloride again, same chemical. And here's our amide. So we're producing ethan amide here. Vigorous reaction again, hydrogen chloride gas is produced, so it must be done in the fume cupboard. So the reaction with alcohol produces esters. So let's have a look. So there's our alcohol there. So ethanol chloride plus alcohol. This is methanol we're using here. And we're producing our ester. As you can see, this is methyl ethanoate that's produced. And again, white misty fumes is produced. And make sure that's done safely. And the last one. So it's the reaction with primary amines produces N-substituted amides. Sounds a bit of a complicated one, doesn't it? So here we go. Here's our ethanol chloride again, and there's our primary amine, and we're going to react them together, and we're going to produce our amide. Now, when we're naming it, this is a little bit tricky. We always start with the letter N, because N represents the nitrogen that's actually on there originally. So that nitrogen is on there. Okay. Methyl is the group that is attached on here. So it's very similar to an ester when you're naming an ester. So we name this bit first. Okay, so it's N-methyl, and then it's ethanamide, which is this bit here. Okay, so it's two carbons, so it's ethan, and it's amide because we've got this NHC double bond O group here. So it's N-methyl ethanamide. So when we say N-substituted amides, the substituted bit is what has been substituted for the hydrogen that would have otherwise have been there if it was a straightforward amide. So normally this amide would have two hydrogens on, but one of the hydrogens you see has been substituted for this methyl group, so it's called an N-substitute amide. So whatever the substituted bit is whatever this bit is here. Okay, anhydrides. Now these are another derivative of a carboxylic acid, so they're formed from a similar method, but anhydrides are actually molecules that are made from two carboxylic acids that are the same, and they're the only type that you need to know for OCR. So acid anhydrides are made by naming, named by naming the known carboxylic acid it's made from, and removing the acid word and adding anhydride on the end. So let's have a look. Here's the first one. So you can see here, it looks a little bit like a carboxylic acid. Now, you can see it here. If we kind of chop that bit off there, if we chop it off there and ignore this bit, you can see it looks like a carboxylic acid, but we haven't added a hydrogen on. Basically, we're missing a hydrogen, and instead we bolted on another carboxylic acid onto the middle there. So this is called ethanoic anhydride, because it's made from ethanoic acid, as you can see. And because the other branch, even though you might think, well, hang on, there's 4 carbons there, surely that should be bute. When we're naming anhydrides, we only pick one of the carboxylic acids, if they are the same, of course. It's different if they're different, but you don't need to worry about that for OCR. So this one, we just name it, find one of the ethanoic acids, one of the carboxylic acids, and we just use that there and just put anhydride on the end. So it's as simple as that. So anhydrides do react with alcohol as well. Very similar to acyl chloride reactions, but they're less vigorous. They're nowhere near as reactive. So let's have a look. So there's our acid anhydride. So this is ethanoic anhydride that we looked at before, and this is going to produce. This is going to react with our alcohol. In this case, we're going to react it with methanol, and what we produce is methyl ethanoate. So we're producing our ester, just like what we did with our acyl chlorides. You would produce an ester, but the other product we produce is actually a carboxylic acid. We don't produce HCl. So the products of this are much safer. The reaction is nowhere near as vigorous, but it's a lot safer than using acid chloride. So esters are formed by a reaction of acyl chlorides with phenol as well. So remember, when you form an ester, normally you would use an alcohol to form that. So a phenol is very similar to an alcohol. And again, if you're not too sure what a phenol is, I have done a video on benzene and phenols on Allery chemistry, so go and have a look there. But there is a video that looks at that as well. Look in the playlist, the year 2 playlist. So esters are normally made from alcohol and carboxylic acids, but phenols react slowly with carboxylic acids, so they're not as vigorous. So reacting with acyl chlorides are much quicker at room temperature. So this could be quite favourable for chemists. So here's our acid chloride again. This is ethanoyl chloride. And what we're going to do is react that with our phenol, which is there. And again, I've colour-coded the elements so you can see where the elements are going. So here's your phenyl ethanoate. So that's your phenol that's been reacted with your ethanol chloride. It forms your ester. So you can see here the ester part comes from your ethanoyl chloride. That's this bit here. And everything else comes from your phenol. What's produced is HCl, hydrogen chloride. Exactly the same as what you would do with a standard alcohol. We are still producing hydrogen chloride gas. Okay, so let's look at the formation of esters. This is esterification. Now you might have seen some of this at GCSE. It depends on the syllabus that you've done. But we're just going to go through the basics of this first and then build that up. So if we react an alcohol with a carboxylic acid and anhydrides, these can be used to make esters, and they have the carboxyl. They have the carboxyl. They have the ester group, the ester link, which is COO link. So an ester is produced when we react a carboxylic acid with an alcohol, and we use a sulfuric acid catalyst. So an ester is also produced when an acid anhydride reacts with an alcohol, but we'll look at that a little bit later on. So you might have done this, like say, as a practical, and they got this nice. Some of them have got nice smells, like pear drops, oil of wintergreen. Some of them have got rancid smells, like rancid butter. But esters actually have a big part to play in reactions. So you can see here we've got in food production, should I say. So you can see here we've got our carboxylic acid. It's reacting with our alcohol, and we form our ester and water. It's a reversible reaction, and we use our acid catalyst, as you can see on there. So there's your carboxylic acid plus your alcohol will form your ester, and water is produced as well. So if we look at that with an anhydride, it's very similar to a carboxylic acid. The only difference is we produce an ester and carboxylic acid. We just don't produce any water at the end of it. So we're getting 2 products out of this one. So esters are named in 2 sections. Okay, so just like when we looked at naming an acid chloride, we can name an ester in the same way as well. And again, you might have seen this already at GCSE. But the first bit is named from the alcohol that's used, and the second bit is named from the carboxylic acid that's used. So let's have a look. So reacting ethanol with propanoic acid, and we form this ester here. So what we're going to do is we're going to name this bit first. So this is formed from the alcohol group, and the alkyl group in this case is ethanol. Okay, so this is your alcohol group, the alcohol that we used. So this is named first, and then the second part has come from the carboxylic acid, and all we do is remove the oic acid bit, and replace it with O8 instead. So in this case, this is called propanoate, and is named second when we're naming an ester. So the full name is ethyl propanoate. So because it's from ethanol, so we take the ol off and put "-yl", and then the last bit is propanoic acid. We take the oic acid off and put O8 instead at the end. So this is called ethyl propanoate. So here's another example. So this is reacting ethanol with 2-methyl propanoic acid. So it's a bit more of a complicated example. Okay, so what we're doing when we name esters, when we name esters with an alkyl branch, we number the carbons in the COC part as well. Okay, so we've got 1, 2 on this side. There it is. And we've got 1, 2, 3 on this side. So we name them separately. So this part of the ester is from the alcohol, and we call this ethyl because it's ethanol. And this part of the ester is from the carboxylic acid, and this example is called 2-methyl propanoate, and this is the second part because that methyl group is sitting on the second carbon. So the full name is ethyl 2-methyl propanoate. Okay, so make sure you're able to name these esters and know how to and which order to name them in, excuse me. Okay. So let's look at hydrolysis. So obviously we know how to make an ester. This is actually going backwards. So esters can be hydrolyzed. Now hydrolyzed means splitting with water. So hydro meaning water, lysis meaning to split. Okay, so hydrolysis. So these can be hydrolyzed. However, it can be sped up using an acid. So we call it acid hydrolysis, or a base, and we call that base hydrolysis. So let's look at acid hydrolysis first. So here we're using dilute acid to split the ester into a carboxylic acid and alcohol. So all this means is we're just going backwards. We're just reversing the reaction. So we can use sulfuric or hydrochloric acid, and it must be conducted under reflux because they've got some volatile compounds here and we don't want any lost. So here's our ester here, and again I've colour coded it, we've split it up, and we've got water because we need water, it's hydrolysis, but it's dissolved in acid, and that's what the H plus bit here is there for, because it's an acid hydrolysis. So we form our carboxylic acid, so you can see the OH bit in green comes from the water, and the CH3CO bit comes from the red bit of your ester, so you can see how that's split up. And then we form our alcohol back as well, and our alcohol is formed predominantly from the alcohol part of the ester, and the hydrogen as well that's attached on the end there, so you can see that. And so the addition of more water, if we add more water to this, it shifts equilibrium to the right, and so more product is produced. So it's a good way of, if we just put more water into this reaction, we get more product that's produced because it is in equilibrium. So this is from Le Chatelier's principle. So if you're not too sure about that, go back and have a look at the how far video that I've done, and that talks about Le Chatelier's principle in a little bit more detail. Okay, so now we're going to look at base hydrolysis. So here, instead of using acid, we use a dilute base to split an ester into a carboxylic acid and alcohol. We're still forming the same products, we're just using a different reagent. So the reagent we're using is sodium hydroxide, and again, it's still conducted into reflux because the reactions that we're doing are quite volatile. We don't want to lose any. Reflux allows us to heat something without losing some of the reactants or products. So there's our ester, but this time we're going to use OH minus ions. So we form this product here. This is our ion. So you can see here we've got the this bit here, which is our CH3CO from the carboxylic acid part, and the oxygen here comes from the base. And then you can see here that we've also got our alcohol formed again. The hydrogen comes from the base, and the blue bit comes from the rest of the acid, rest of the ester, should I say. Okay, and that's it. And so that summarizes the carboxylic acids and ester topic for OCR. Please subscribe to my channel. There's loads of videos on. There's a full range of videos, like I say, for OCR and for other exam boards as well, that covers the full syllabus. So please have a look and see what you think. There's going to be more added on there, so if you subscribe, you can get all the updates. And also, if you want a copy of these PowerPoints, then you can click on the link in the description box, and you'll be able to purchase them from my test shop. They're great value and great for your revision. Okay, that's it. Bye bye.